Hey guys, this is my solution to USACO 2024 February contest bronze problem 3. If you want to skip to the logic or code, the timestamps are on the screen. Otherwise, I will start reading the problem. So Farmer John has n farms numbered from 1 to n. It is known that Farmer John closes farm I at time ci. Bessie wakes up at time s and wants to maximize the productivity of her day by visiting as many farms as possible before they close. She plans to visit farm I on time ti plus s. Bessie must arrive at a farm strictly before Farmer John closes it to actually visit it. Bessie has Q queries. For each query, she gives you two integers s and v. For each query, output whether Bessie can visit at least v farms if she wakes up at time s. Alright, so it seems the first line of input is n, the number of farms, and q, the number of queries. The second line is c1 to cn, which basically tells the times at which farm I is being closed. And the next line is telling us at ti, so at which time Bessie's planning on visiting the farm after she wakes up. So, and the next Q lines are the queries, with the with the first integer being V, which is asking if Bessie visited at least that number of farms, and S, the time at which Bessie wakes up. So, if we summarize what just happened here, so we're given Q queries. For each query, we have to find out whether it is possible to visit at least a specific number of farms, which is V, the first integer, based on what time Bessie woke up, which is S. Uh, So we checked that this is all based on what time the farm closes, and after what time after Bessie wakes up, she's planning on visiting the farm. So let's look at through the example here. So we have 5 farms and 5 queries, and these farms close at times 3, 5, 7, 9, and 12. So what we're basically doing is for each query, let's look at the first query. The first query, so query 1. Query 1 is basically telling us V is 1, which is asking, did Bessie visit at least one farm? And 5 is telling us that if Bessie woke up at time 5. So let's write out T as well. So T would be 4, 2, 3, 3, and 8. All right. So what we're basically doing here is we're adding S, which is 5, to each of T, like T1, T2, so forth. And we're checking if that's strictly less than C. Because if it's greater than, that means the farm has already closed, so Bessie cannot visit it. If it's equal to, that means it's at the time of closing, but Bessie cannot visit the farm at the time of closing. So if we look at the input here, if we add 5 to each of these, then this would become 9, 7, 8, 8, and finally 13. So if we compare the first line with this, the only time when Bessie could actually visit a farm is this time of the fourth one, because this is exactly less than this. So Bessie can visit exactly one farm. And if we look at the query, it's asking did Bessie visit at least one farm, and it did. So yes, that's correct. Let's look at some more of these inputs. So next line is query 2, sorry, and it's asking 1 and 6. So if we add 6 to each of these, we get 10, 8, 9, 9, and finally 14. And if we compare this to the time at which the farms close, we see that none of these are less than when the farms close. You might be thinking, but here they're equal, but they cannot be equal because if they're equal, that means Bessie visits the farm at the time of closing, but that's not possible. So we have to basically check how many farms Bessie visited. If that's so, farms Bessie visited has to be greater than or equal to V, and if that's true, we output yes, else output no. All right, we got the logic down. So let's look at how we can solve this problem. Uh, so the brute force, first is the brute force. It's gonna be O and where. So the brute force solution is, you might be thinking, so we have Q queries. Why don't we just create a temporary array, like basically what we did here? So sorry, why don't we create a temporary array, like for example, for the first query, which is 1, 5. Let's add S, which is 5, to each element in the t. So 5 plus 4, 5 plus 2. Basically copy this. I can't. So we have 9 and then 7, 8, 8, 13. We just copied over. We just added 5 to each of those elements, and we got this, produced this new array. And then we go through C of I, which is 3, 5, 7, 9, 12. And we compare each of these elements and check if it's less. And checking if they're less is going to be AND operations, because you go through the array exactly once, so you're going through each element in the array and you're checking if it's less. And if you look at it, we're doing this for Q queries. So the time complexity of this algorithm would be Q times N. And if we look back at the problem, we see that Q is 2 times 10 to the 5th, and N is 2 times 10 to the 5th. That means our algorithm would be 4 times 10 to the 10th. But that's not what we want. This will result in a time limit error if we do try this. So now is the optimized solution. It's the binary searching through, and this will lead us to an n log n solution. If we look at our array C, and then we look at our array T. Okay, let me add more spacing. That's better. You can see that the values C and T never change. The only thing that changes is S, because as we go through the queries, only S changes, but C and T never change. So we can create an inequality actually. So we know that T of I plus S of I has to be less than C of I. So T of I plus S has to be less than C of I. Or the other possibility is T of I plus S is greater than or equal to C of I. But this will not work, because this means that Bessie will visit the farm at the time or after closing, but that's not what we want. We're checking for T of I plus S is less than C of I. So we can solve for T here by algebra. So this becomes I minus T of I. So we can, if we look here, we're basically taking the difference of C of I minus T of I, and this will always remain constant because our C values and our T values are always the same. So with this knowledge, we can create a difference array, an array that holds the differences between C of I minus T of I. So if we look back to the first one, we can create this difference array. So we'll be subtracting C of I minus T of I. So if we look at the first one, it's going to be -1, then 2, 3, then 4, then 6, and finally 4. So this array will always remain constant, and we can check for what values of S will give us something that's greater than C of I minus T of I. So a trick we can do here is sort this array so that the differences are in increasing order. So if we sort, we will get -1, 3, 4, 4, 6. -1, 3, 4, 4, 6. Now we have to find a value in the array that is strictly greater than S. Remember, it can't be equal to, otherwise we'll be arriving at the farm at the time of closing. Now we have to find a value in the array that is strictly larger than S. This is because if you think back to the inequality, S is less than C of I minus T of I. In order for us to get to the farm before C of I, we have to find a difference that will get us above S. So if you think about it, we're checking if our S value is small enough so that we can reach farm I before closing. So what the difference array basically tells us is how much time we have from T of I until the farm closes. So as we increase, this gives us more flexibility. So we're only checking if our S value is small enough so that we can reach farm I before C of I. So we have to find a value that is strictly larger than S since the array is sorted. Because if you think back, we will reach the farm at T of I plus S. So we have to find a value larger than S. So this gives us enough time to reach after s time. So if you look back, the only value that is greater than s here for the first query is 6. Sorry, is 6. And if we know that an element is larger than s, then every element after, well, not in this array, but we know that every element after must also be greater than s because this array is sorted and is in increasing order. So we can calculate how many elements are from the end to this element to check how many elements are greater than, to check how many farms that Bessie has visited. And then finally, we can compare the amount of elements with phi. So we can compare amount of farms visited, and we check with if it's greater than or equal to phi. And this will basically tell us if Bessie has visited enough farms. Now for finding the first element strictly larger than s, the brute force method would be to go through each element. Let me rewrite it. So -1, 3, 4, 4, 6. The brute force way to do it is check through each element. So 1, 2, 3, 4, 5. Check through each element until you find an element that is strictly larger than s. This will take at most of n operations, which is not what we want. So, but since we know the array is sorted, we can use binary search. And this will give us O of log n. And this will give us O of log n, time complexity. So if you look at our total algorithm, this will be Q queries, so Q operations. This will be Q queries, Q operations, times log n. And this will be fast enough to run. So for binary searching, in C++, there's a nice function called upper bound. And this basically returns an iterator to the first element that is strictly greater than the value we're searching for. This function uses binary search, so it has a time complexity of O of log n. In other languages like Python and Java, you'll have to write your own binary search algorithm out. I will show you how to do so. Alright, I've opened up my IDE, and this is just a basic template of getting the libraries and faster input, output. I've listed out the 4 main tasks: input, creating the difference array, sorting the difference array, and finally binary searching. Alright, let's get started with the input. So first we take in two integers n and q, and then we create an array. A vector is just an array list, just remember that, of closing time, which is c, and then just the time that Bessie decides to leave. So this is c and t, and this is n farms and q queries. Okay, and this just means you're creating the constructor of n elements. So then we can take input, and we're taking the input of these two arrays, and then we can create in C++, there's something called pairs, which is basically two elements in an array, and we can call this queries. So let's go through the Q queries, and for each query, we're taking in V and S, and then we're creating the pairs with V and S, and that's it for our input. Now it's time to create the difference array. So our difference array, So we will go through the n elements, and then we will push back, which is add an element. We're gonna add the differences between C of I and T of I. And then that's done. And then we can sort the difference array. And our array is sorted. And now we're going to start binary searching. Now, C++, as I said before, C++ has the function upper bound, which returns the iterator to the first element that's greater than the element we're searching for. That's exactly what we want. But languages like Java and Python don't have that. I will show you how to do it manually in a second. So what we want to do is go through every single query, because every query has one answer. and that we will output like here. We want to output yes or no if Bessie visited enough farms. So we go through Q queries. So as less than Q I plus plus. So we're going through Q queries here. And what we want is we want an upper bound. It's just auto because it's an iterator. We want upper bound. So the beginning, we put in the beginning of what we want to search, which is the beginning of the array, and then the ending of what we want to search, which is the end of the array, and the value we want to search. And this is the second element, because remember, if we look back to our input, the second element we input is S, which is the time she wakes up. So we want to search for the first element that is greater than S, and this does that. And then we want to find how many elements are greater than or equal to this element, because every element after this element is also greater than S, because the array is sorted in increasing order. And we can do this by subtracting this total size of the array with the amount of elements that came before it. And this would be, here's the code. What this does is it returns the index of the upper element, and then n is the size of the array. And subtracting this gets us how many elements are after the index. So, for example, here n was 5. And subtract that with the iterator is going to give you, so it's just 0 index by the way, so 0, 1, 2, 3, 4, and it's going to give you 4 minus 0. It's just to return the integer. We do this to return the integer, and this is going to give us 1. And that's true because Bessie was able to visit exactly one farm before. Alright, so let's just call it cutoff for, and this would be n minus upper minus diff array again. Remember, this subtraction is just to give us the integer. We're basically just subtracting by 0 just to give us the integer because it was an iterator before. And then what we can do is we check if the amount of elements, which is cutoff, is greater than or equal to queries of I dot first, which is basically the v value here. We're checking if it's at least has visited at least that many forms. We print yes. Otherwise, we print no. And that's basically it. So if we build this, if we build it, paste, and we can check, yeah, it works. So now this is for C++, the upper function. But what if you wanted to use, what if you want to create it manually, like a binary search manually? So what we can do is we can use the traditional while loop. So we set our lower bound, which is 0, and our upper bound, which is the last element. So remember, this is 0 index array, so you subtract 1. And you check while low is less than or equal to high. You're going to binary search, so you create a mid, which is going to be low plus. It's just finding the middle of these two. And then if the middle is greater than S, you want the high to come back. You want the high to come back. Else, if it's less, then you want the low to come up. So low is going to come up. And then your low would be the correct answer. And then your cutoff would be n minus low. What low will become the index to the first element that is greater. The first element that is greater than S. And cutoff is basically the same logic as before. And if we check, we can copy paste this. If you look, it works perfectly fine. And if we submit it, it gives us the correct answer. All 17 test cases. Thank you.